Hey guys, today I wanted to wrap up the last of the series of our makeup videos here and also wrap up the last of the new sections from our series unit. Today we'll be talking section 9.3. This is on Taylor series. Okay, so this is basically the last of the new stuff that we'll be looking at for the rest of the semester. Now, to get started here, wanted you guys to recall a few things because Taylor polynomials are things we've worked on before. Power series are things we've worked on before. I've mentioned very briefly what a Taylor series is, but we'll go ahead and piece these together. Remember, power series, these are anything of the form sum ck times x minus a to the k. Okay, whatever your indices are, by default, I'll just assume 0 to infinity. These ck are going to give us coefficients on our power series. You guys also had a formula for your nth Taylor polynomial. What this looked like was going to be a sum from 0 to n, so your degree of your polynomial tells you where to stop in your sum, of this guy. Okay, you're taking a kth derivative of f at a over k factorial times x minus a to the k. Okay, and both of these guys, these are either a series or a polynomial. They're centered at a. Okay, so this a value is telling you where you're taking your series or your polynomial. Here for your polynomial, the n is going to be telling you the degree, okay, so where you stop. Now, I've already given this formula you guys once before. We haven't done too much with it aside from one or two examples because we've mostly done manipulations of series we know rather than new power series. If you piece both of these guys together, you're going to get the following, right? So you have seen this before, the Taylor series, okay, for a function f of x centered at x equals a. This guy is given by the following. I'm going to go ahead and call this guy t of x. Basically, we're piecing both of these things together. Okay, this is a polynomial because it stops. Okay, so if you're second or third degree, you stop the second or third term, so it's a second or third degree polynomial. Power series don't stop. But, your general power series definition, they didn't give you much information on what was going to be happening with the ck. For combining both of these, steal this Taylor polynomial coefficient to help you figure out what your power series coefficients are. Okay, so this is kind of like mushing both of these formulas together. Your coefficients and your series, these are all going to come from the same formula that we had for Taylor polynomials, right? So we'll look at my kth derivative of f at a over k factorial times x minus a to the k. Basically, this is the exact same formula as we had up here, except for you keep going, right? So this guy is going to be infinite degree. Okay, same formula as my Taylor polynomials, but okay, they're infinite series this time, not finite series. Okay? So, if I'm computing these things, here's kind of the trick, right? We've looked at Taylor polynomials before, and our usual means of trying to write these things out were, we would write out the formula that we needed up to the term that we wanted. That would tell us how many derivatives we would need to take, and we would have to take all those derivatives and plug them back in. We can't do that here, though, right? Because if we're taking an infinite series, we're not going to take an infinite number of derivatives. So the new trick, okay, for today is instead of, taking all the derivatives that we need, because we're obviously not going to have time to do that, we're going to take as many derivatives as we need to try and get a feel for a pattern for this coefficient. And then once you get a pattern for what your derivative is, and once you can kind of come up with a formula for it, then we're going to go ahead and stick stuff back in the formula to get our Taylor series. All right, so the big idea for today is look for a pattern in your derivatives, okay, to use this formula. Okay, so I'll try and start off with one that's not too bad. Here, let's see if we can find the Taylor series for the following function. Let's take a look at 5 to the x, and we'll have this thing centered at x equals, let's say, 2 here. Why not? Okay? So, again, notice what's going to go on in my formula. Okay, we're taking a sum from 0 to infinity of my kth derivative at a over k factorial over x minus a to the k. Since this guy's centered at x equals 2, this is telling me basically what my a is. So, really, what I'm looking for here is, if I stick my a in, I need a kth derivative at 2 over k factorial. This is going to be times x minus 2 to the k. And now, the thing that I'm going to be looking for is, what the heck is this thing, right? What happens when I take a kth derivative at 2? Okay, everything else in this formula is pretty explicit, right? And this kind of matches up what we were saying for our power series, right? You need x minus a to some power, and then you need a formula for your constant coefficient that goes alongside of it. And since I don't know what my kth derivative of f is, I really don't have my formula explicitly here. So that's what we're going to be looking for. My goal is to take my derivatives and then look for a pattern. Now, if you don't remember your derivative for your general exponential function, notice this is something of the form a to the x that we're looking at here, okay, number to the x. This guy had the derivative rule that whenever you derive this, it looks like you take the original function, a to the x, and you multiply it by natural log of the base, right? So this looks like natural log of a times a to the x, right? And this natural log of a, this is just a number, right? Take 5 here, for example. Stick it in your calculator. By taking a natural log of it, you'll get a number back. So this is some constant times a to the x. Right? So if I'm taking derivatives here, we are starting with the function 5 to the x. That means when I take my first derivative, this is going to be natural log of 5 times 5 to the x. Remember, the way that your constant coefficients work when you're taking derivatives is you hang on to a constant coefficient and then you multiply by the derivative of the rest. So here that'll tell me f double prime is, I hang on to this, and then I multiply by the derivative of 5 to the x, which is, natural log of 5 times 5 to the x. And we're going to have to do the same thing again next time, right? If I'm taking my third derivative, I have to hang on to my constant coefficient, and then I have to multiply by the derivative of my remaining function, which is going to be natural log of 5 times 5 to the x. We said we're taking derivatives and looking for the pattern. Hopefully the pattern's pretty clear here. We started out with 0 copies of this natural log of 5 as our coefficient. On the next round we had 1, on the next round we had 2, on the next round we had 3. So if I'm looking for a general pattern here, notice that whatever derivative I'm taking, 0th first, second, third, etc., this is going to dictate how many copies of these natural log of 5s I have. Okay, so if I'm looking for a pattern for fk, or my kth derivative here, my pattern is that I have k copies of natural log of 5 each time. Right, so this is natural log of 5 to the k, okay, to tell me that I have my k copies, and then I have this 5 to the x on the end. Okay, now remember, to use this formula, we have to figure out what the heck my kth derivative at 2 is. Well, if I'm trying to figure out my kth derivative at 2, I just plug 2 into this function, right? So my kth derivative at 2, this is going to be natural log of 5 raised to the k times 5 to the 2, or times 25. So that means when I go to take this guy back to my series, okay, my desired Taylor series is basically going to be this thing with my appropriate pattern for my derivative plugged in. So I'm looking at my sum from 0 to infinity of, we said this is my kth derivative at 2, so this guy's going to go right on in here. Okay, we've still got the k factorial, and we've still got the x minus 2 to the k. Okay, this is what I'm looking for as my final answer. So if you wanted a series representation of this guy for whatever reason, you know, maybe to anti-derive or do other things like that with, maybe if you wanted to use a finite sum of this for an approximation, whatever you were looking for this for, you know, taking limits, doing other things, this is what we're looking for our Taylor series. Okay, and you know, if you wanted to find intervals of convergence or things like that, you could go back to what we were doing last class in section 9.2 and apply it to this formula to find your appropriate interval of convergence. Okay, I'll try another example here. We'll try one that's kind of familiar. Let's go ahead and use my Taylor series formula to show that the Taylor series for the function 1 over 1 minus x centered at x equals 0 is, well, we've worked with this before. We've said over and over and over again that this just looks like x to the k. And we actually spent you know, most of a full class manipulating functions that kind of looked like this, using this formula to get series back. Okay, well, this is one of the reasons we can do this. We argued before that this worked because of geometric series. You can show that the formula that you get back is still x to the k, even using the Taylor series formula. Alright, so again, we are starting with my sum from 0 to infinity of my kth derivative at a over k factorial times x minus a to the k, or here, since I'm centered at 0, this means that a is really 0, so I'm looking at my kth derivative at 0 here over k factorial, and if I have x minus 0 to the k, subtracting 0 just gives you x. This is going to be x to the k. Okay, so again, the catch that we're looking for here is, what is this derivative? Okay, again, we're looking for my pattern in my derivative to be able to stick stuff back in the formula, okay, and hopefully we can show that it comes out to this guy, right? So, we've kind of done a Taylor polynomial of this before, so I'll try and fly through the derivatives since we've seen this at least once. They said it was a little bit easier to think of this as 1 minus x to the negative 1 and hit this with chain rule to try and pick out a pattern, right? So my first derivative is going to be negative 1 minus x to the negative 2 times negative 1. These negatives we're going to cancel. Okay, so I basically just get 1 minus x to the negative 2. Similar deal over here for f double prime. This is going to be, chain rule on this, negative 2 times 1 minus x to the negative 3 times negative 1. My negatives cancel. So I'll get 2 times 1 minus x to the negative 3. You might have an idea of where the pattern's going from here, but if you're not 100% certain, I would say to just try and keep taking derivatives until it really jumps out at you. And I'll try just a couple more so we can really nail this down. Okay? Here, again, chain rule, I need to bring down this minus 3. So this will be 2 times minus 3 times 1 minus x to the minus 4. Chain rule says multiply by the derivative of the inside, which will cancel my signs. To make the pattern super, super clear here, I'm not going to multiply stuff out yet. Okay, so I've got 2 times 3 times this thing with the power. Okay, for my fourth derivative, chain rule one more time, hang on to your constant coefficients, and you have to do chain rule on this. This means I'll be bringing down that minus 4, taking 1 minus x to the minus 5. Derivative of the inside is minus 1. My signs will cancel. And again, to really nail down the pattern here, I'm not going to multiply this out yet. Hopefully you guys can kind of see what's happening, right? A couple things that are going on. First off, I've got this 1 minus x every single time. It's being raised to a power every single time. Okay, and we can notice that this is kind of incrementing by unit. Okay, we started at minus 1, went to minus 2, minus 3, minus 4, minus 5. You can kind of see that each time we hit this with power rule, it's going to decrease by 1. And then the other pattern that I've got going is look at what's happening to the coefficients. Okay, this, if I want to fill in coefficients to help me with my pattern matching a little bit, you notice we have this 2 times 3 times 4, 2 times 3, 2. If I filled a 1 in here, it should be really clear that what we're doing every time is we're taking a factorial, right? This is 4 factorial, 3 factorial, 2 factorial, 1 factorial, and if you remember, 0 factorial was just 1, so even this first term still fits that pattern. Right? And a nice coincidence is the factorial that we're taking, it happens to match whatever the heck derivative we're doing each time, right? So 4 and 4, 3 and 3, etc. Right? Even up here we're taking the 0th derivative, so that was a 0 factorial. Right? If I'm looking for a pattern, my kth derivative hopefully is going to have, like we just said, a k factorial out front. We're going to have a 1 minus x here, and we're raising to some pattern. First off, every single time, my exponents were negative, so I'll throw that negative sign in here. And if we want to know what the pattern was, try to think of what your pattern is as a function of whatever derivative you're taking. Okay, so if you're taking a kth derivative, how do you get back to this number from your k? Right here, my fourth derivative, this is negative 5. My third derivative, this is negative 4. My second, this is negative 3. Okay, so the absolute value of this, okay, you know, once I account for this negative sign each time, it's 1 bigger than whatever my derivative is. Okay, so I can think of this as minus k plus 1 up top. Okay? And, again, for me to use the formula, I need to figure out what's going on at 0. Okay, not a generic x here. Okay, so this is, you know, my kth derivative at x. If I need to use the formula, I need to take my kth derivative and then plug 0 in. This is going to be k factorial times 1 minus 0 to the minus k plus 1. Well, this is really 1 to this thing. What's 1 to anything? Anything is 1. So my kth derivative at 0 is k factorial every time. We can take this, stick it back in my Taylor series. Okay, so my Taylor series is going to be my sum from 0 to infinity of this derivative that we just found, k factorial, divided by, and then you copy everything else over. And the reason, okay, why we got this x to the k that we were expecting before using the geometric series formula, you can do cancellations. Okay, so we do our cancellations, and we get back exactly what we were expecting. Right? Now, a couple notes for this, and that I should mention. One, kind of like we've been working with a lot so far, we very frequently center these things at 0. Okay, a reason for that, it makes plugging stuff in really easy a lot of the time. So it's something that we actually do pretty frequently. Since we do it so frequently, it gets its own name, right? Since A equals 0 is a really common location to center things, this case gets its own name. Okay? And fast definition here. The Maclaurin series of a function, f of x, this guy is basically the Taylor series of f of x centered at a equals 0. Okay? You notice anytime that you are given a Taylor polynomial or a Taylor series or a power series, you always have a location that you're given that this guy is centered around. If you're told to take a Maclaurin series of something, they're not going to give you a number because they're going to expect that you know this definition right here and know that A is going to be 0 automatically. Okay, so anytime you read Maclaurin series, think of it in your head as figuring out whatever your Taylor series is for that same function, but just do it at 0 automatically. Okay, assume that A is 0, even if you're not given a number. Okay, you can try an example here. Let's say that I want to find the Maclaurin series for the function cosine of x. Okay, again, this guy is going to be automatically centered at 0. So this means that the formula that we're using automatically centers things at 0, right? So you're taking a derivative at 0. The k factorial doesn't change. If you're doing x minus a to the k, this is x minus 0 to the k. So we're basically starting here. What we're looking for in this case is now going to be the pattern that pops up when you take derivatives at 0 for this function. Okay, and we know the trig functions have these nice cyclic derivatives for us, right? If I'm starting at f of x with cosine, this is giving me an f prime of negative sine x. This is giving me an f double prime of negative cosine x. And this is giving me an f triple prime of basically sine x. And then this thing repeats afterwards, right? So we cycle. Your derivative of sine is cosine, and this kind of keeps going. So, if I needed the pattern here, remember, if I need to plug 0 in, you're going to look at your f0, f prime of 0, f double prime of 0, f triple prime of 0. Okay, and if we go back to our unit circle values, cosine of 0 is 1, so that'll give us both of these guys. Sine of 0 is 0, so that'll give us these guys. So my pattern is again going to loop. If I want to look for a solid pattern in all of my derivatives here, this is going to go 1, 0, negative 1, 0, 1, 0, negative 1, 0 forever. Okay? Now, the last couple of examples that we did, we had a nice explicit formula that we wrote out for trying to, write in this f of k of 0. Sometimes it's not easy to come up with a nice explicit formula. So what I might suggest here is let's see if we can actually kind of write this out, okay, for the first couple terms, right? What was going on here is if I stick in 0, right? Let's try to expand my formula to look for my pattern. Okay? If I try to expand my formula to look for the pattern, okay, my zeroth derivative, okay, again, I'll go ahead and write this up top here. We want my derivatives at 0 over k factorial x to the k, and you know that your derivatives loop, right? They go 1, 0, minus 1, 0, etc. So when I plug in 0, okay, this is going to be my 0 derivative over here, 1 over 0 factorial, x to the 0, plus, if I plug in k equals 1, there's going to be nothing. If I plug in k equals 2, this is going to be minus 1 over 2 factorial, x to the 2. If I plug in 3 for my third derivative, I'm multiplying everything by 0. And then this is going to loop, right? If I plug in 4, this is going to be plus 1 over 4 factorial, okay, x to the 4. If I plug in 5, we're looping back again. So this is 0. If I plug in 6, that'll correspond to this guy. So hopefully we're maybe starting to see the pattern here. All of the odd derivatives, since this was a 0th derivative, this is a first, a second, and a third. Fourth, a fifth, a sixth, a seventh. All my odd derivatives completely drop out because they gave me 0 coefficients everywhere. And all my even derivatives stick around. So if I clean this thing like, 1 over 0 factorial x to the 0, watch my sign here, 1 over 2 factorial x squared, 1 over 4 factorial x to the 4th. Okay, and notice the other thing that's emerging here is because our derivatives, the non-zero ones, alternated between positive and negative, these are going to alternate between positive and negative. So I'll expect that this next even term is going to be a plus term, and I'll expect that my next even term after that is going to be a minus term. So, this is kind of like one of the cases that we were mentioning before when we were trying to come up with patterns for series. Said it was kind of hard to come up with an explicit formula off the bat, so we could try and write this out and look for a pattern here. Alright, well, you notice every single time we have got a factorial in the bottom, plus or minus 1 up top, and a power of x. Okay, so if I try and get my series here, we have got a factorial in the bottom. Notice it's always an even number, though. So I can't just stick k factorial down here. I'm going to shove a 2k down here to make note that this has to be even every time. Okay, and the power on the x usually matches whatever the heck that number is. Right? Now the last component here is there's either a plus or a 1, plus or minus 1 up top. Well, let's think about where our indices need to start so we can make sure that we get the power on that straight. For me to get this first start term, I need to start k equals 0. And if I'm thinking about minus 1 to either, the k or k plus 1 or something like that with an offset, well, I'm starting out with an even power. I needed to start out positive. Starting out with just the k power is going to be fine here. Okay, so my Maclaurin series for cosine is going to come out to this guy. Alright? Now go ahead and throw another note at you guys. Much like our series from before, okay, you can manipulate power series we know to get new series. Okay, and the tricks that we had before were things like addition, we used multiplication, we used composition, we also used integration and differentiation as tricks. Okay, so I'll try and do an example like that. Let's see if we can find the Maclaurin series for, I'll look at the function, let's try sine of x, okay, using this previous example results. So, basically this last example, we came up with the idea that cosine was supposed to be, if we go back and just, look a couple lines up in our notes, we had minus 1 to the k over 2k factorial times x to the 2k. Now, if I'm thinking about operations to, perform on this to get sine back, what can I do to cosine to get sine? Well, not plugging stuff in or adding stuff to it or, multiplying. The integration or differentiation operators are probably going to be pretty useful, though. If you derive this, you get negative sine, which you could do that, but we'll be off by a sine error. If you integrate this, you get sine, right? So what I can try is to integrate both sides, because then I should get sine on both sides, right? Now, to do this, we mentioned you can go straight from this formula, or you can try to write it out a little bit. Okay, so we said this is basically 1 over 0 factorial. Okay, if I plug stuff in, x to the 0, so, 1, minus 1 over 2 factorial, x to the 2, plus 1 over 4 factorial, x to the 4, minus 1 over 6 factorial, x to the 6th, plus so on and so forth. If I integrate both sides of this, I could either, integrate this term by term by term and look for a pattern there, or I can try and come up to the formula here and antiderive this guy. Now, I'd recommend trying to do a little bit of a combination of both so you can verify your formula. You'll get sine x plus some constant over here. If I do this term by term, I'm getting x here. Here, I hang on to my coefficient, but I'll get x to the 3 over 3. Notice if 3 is in the denominator, this will really look like 1 over 3 factorial, right? 1 over 2 factorial times 3 is really 1 over 3 factorial. And we're going to get a similar trick happening everywhere else. If this turns into x to the 5 over 5 when we antiderive, if I'm dividing by 5, this thing's multiplied by 5, it'll look like a 5 factorial. Okay, and similar deal over here. So, if I'm looking for my pattern, note what's happening is it's kind of like last time where we've got the alternating plus or minus 1s, and we've got these x to some power over a factorial. Okay, so if I want a straight up formula for this, and if I want to consolidate my C's, we're going to get that sine x should come out basically to something that looks like, come back to the formula here again. You added 1 to the exponent up top, and then you divided by the same number, which increased the factorial that you were taking. Let's see if trying that in our formula matches up with what we just took, right? Hang on to your constant coefficient, and I derive this guy to the x to the 2k plus 1, divide by the same number, that'll up your factorial down here, 2k plus 1 factorial. Okay, and let's verify. If I'm starting with this very first term here, to get x to the 1, I probably had to start with k equals 0. Let's just verify this. That'll give me a positive. This will give me a 1 factorial on the bottom. This will give me x to the 1. Okay, if I plug in k equals 1, this will give me a negative, like my next term, over 3 factorial, which makes sense, and x to the 2 plus 1, which is x to the 3. Okay, so you can verify doing this either from the formula directly or term by term by term. You basically get the same thing. Okay, and just a side note, to match up your C, okay, we suggested fixing the C's a couple classes ago by verifying what happens when you plugged in a value. Okay, note that plugging in x equals 0 to both sides, this guy gives you sine 0 equals the sum of a bunch of zeros plus z. Both of these things are 0. So basically your C here is going to come out to 0 also. If you want your Maclaurin series for this guy, this is what we're looking at. Okay. Now, comments here, just kind of a fast one. We've said before, you can use these Maclaurin series to try and manipulate them and come up with other series. You can use Taylor series and manipulate them and come up with other series. One fast note that I'll go ahead and give you guys, since manipulating series is usually pretty fast, and figuring out patterns and derivatives like we've been doing is pretty slow, okay, is usually faster than finding series from scratch. Okay, you may want to memorize a few formulas here. And these are ones that you won't be given these formulas like on a test or anything, but if you kind of bring them in your head, they'll probably help you out a little bit. And these are all ones that you've done either today or in class earlier at some point. We've mentioned the Maclaurin series for this guy. We derived this a little bit earlier, and we did this with geometric series. This is x to the k. A couple classes ago, we talked about e to the x. Okay, this guy, if you want to manipulate him, this is 1 over k factorial x to the k. And we just did these two. We did sine x, and we did cosine x. Sine x was the one that we just found, okay, like just now, minus 1 to the k, or 2k plus 1 factorial, x to 2k plus 1. Here, this was a sum, minus 1 to the k. This is over 2k factorial, x to 2k. Probably not going to need to memorize much more than this. Anything that you're going to manipulate is probably going to look like you manipulating one of these series. Okay? There's actually a chart at the end of section 9.3 that includes these 4 formulas that you can play around with. And one thing that I'll note, these guys, they're probably pretty easy to memorize. This one especially because it looks like the geometric series formula. This one's not too bad because there's not too much going on in this formula here. These guys are messy, right? And they look kind of close to each other, except for, there's the 2k plus 1s here and the 2k's here, and at least personally, that kind of thing I would usually mix up just because they look so close. I'll give you a tip for remembering sine versus cosine. If you've ever taken a, algebra course where they've referred to things like even and odd functions. Now, this might be dusting stuff off from a really, really long time ago. You've probably heard at least once before that sine is an odd function. Okay? What we meant by odd function is if you plug in a negative to it, you can kind of pull the negative out. And cosine, this guy is an even function. Okay, what I mean by that is, and what you mean whenever you discuss any even function, is if you plug in a negative to it, it looks exactly like you plugged in the same thing as the positive version. If you ever wondered why the heck they called these things odd versus even, because it doesn't necessarily look like it immediately correlates to anything related to odd or even numbers, the power series for these are exactly why these properties are split up as odd versus even, right? Notice what's going on if you plug a negative x value in, okay, to sine, where we have only odd powers. If you're plugging a negative in, you're going to get a negative back. Okay, you know your end result is going to be a negative number. If, on the other hand, you're plugging a negative in to an even function, if you're plugging a negative function into something with a power series with only even powers, you plug a negative in for x, that negative sign is going to drop off because you raised it to something even. So it looks exactly like you just plugged a straight x into that. Okay, so these properties, they really come from the powers that are floating around on these. So match these to your powers. Sine's an odd function. It's going to get the 2k plus 1. Cosine's an even function. This guy's going to get the 2k's. Okay? I'll try and do a really fast example where we maybe manipulate one of these here. So I'll try something kind of similar to what we did with the 1 over 1 minus x functions a while back. Let's see if we can find a series representation for, let's say, 3x times sine of 10x. Okay? What we did with the 1 over 1 minus x examples is you start out with a function that you know. Okay, so sine x, we just said this guy was the odd version. Okay, so we get all the 2k plus 1s everywhere. Oops, 2k plus 1. And what you have to do is figure out how to manipulate both sides to get it to look like this. Right? Now notice one of the things that we did to manipulate this. Okay, this is probably going to be a lot faster than trying to take derivatives and figure out patterns from scratch. Just start with the thing that you know and twist this into this function. Right? One thing you needed to do is plug 10x into both sides. So each time I see an x, I'll plug a 10x in. This will give me that sine of 10x is equal to this guy. Okay, the coefficient doesn't change, but the x sure changes. This is 10x to the 2k plus 1. If you want to split this, you can, 10 to the 2k plus 1, x to the 2k plus 1. The next thing that you really needed to do to make sure that you got this function back, multiply both sides by 3x. Right? Multiply by 3x. So if I do this on both sides, remember we said this is something that my series rules let me push this through by distributive property. Right? So if I want to, what I can do here is you can push the 3 through. You can make this guy be part of your constant coefficient. Okay? The 3 will be part of my constant coefficient. This factorial business with the plus minus 1s will be part of my coefficient. Like we said before, we could split my powers here, get 10 to the 2k plus 1. And then I can also push my x's through. If I push my x through, it's getting paired up with this x to the 2k plus 1. That means that I've now got 2k plus 2 of these on the inside. Okay, so notice this is a lot faster than me trying to take derivatives using power rule and all of that other, business with trying to pick out patterns and see what that does. That would take forever, okay? If this looks really close to something that you already know a series for, okay, usually 1 over 1 minus x, e to the x, sine or cosine, start there, twist it into something that you want, okay? So, that's, for the most part, the tail end of the new stuff. What I wanted to see from you guys next time we run into each other is the following quiz, okay? Let's see if you guys can give me a Maclaurin series representation, okay, of the following. Okay, let's try for the function. Let's do x cubed times cosine of minus x. Okay? While you can sit here and try and take derivatives and figure out the pattern, there's a less painful way to do it. Right? Try to model this after your last example if you want to do this as fast as possible. Alright, so again, this wraps us up on our video lectures. This wraps us up on the last of the new material. If you guys have any questions for me over break, feel free to shoot me an email and let me know. If not, I'll see you guys after you get back, and we'll try and get in on reviewing this stuff prior to the test.